meaning the Chapman's assumptions and his derivation of the formula for ionization or production rate in the ionosphere. Now, I am showing you a figure.
Sir, apuni presentation mode koi diokson, mane view koi diok F5 ba heri koi pelai.
So let us begin from where we left yesterday. Chapman, he assumed that the ionosphere or the upper atmosphere is stratified and it has only one species and it is ionized by solar radiations, monochromatic solar radiation, only one type of solar radiation. Okay. Now, if you look at the figure, figure 1, which I am showing here, let us assume that a bundle of solar radiations or solar flux energy in the form of a tube, which is of unit cross-section coming from infinity. Infinity is the sun. So coming from infinity, and then it is hitting your point of reference. This is the surface of the earth, we may say. Okay, so this is the vertical or zenith, and it is the radiations are coming at an angle chi to the zenith. Okay, and from ground to the height of h, this is the altitude h. The intensity of radiation, because when it is coming toward the atmosphere, it will lose intensity, and therefore what you will see a reduced intensity of the solar radiations, and so that is why it is I now here at the height S. This is the slant height. This is a slant height S. To the with respect to the vertical height h, and this angle is chi, so this is zenith. So chi is the zenith angle. Now normally in case of ionospheric studies, atmospheric studies, we use two angles. One is the zenith angle, the other is elevation angle. So elevation is from I think you know, but still I'm telling you that if I measure from here, this is the elevation angle. This is the elevation angle. It means I am measuring from the horizon. The solar radiations are at an angle of 90 degree minus chi here. Okay, and this is zenith. So zenith angle starts from where zenith means where sun is overhead or your overhead. So this is 0, and the angle is 90 degree here. Okay, so let me go back to the other presentation. Okay. Okay. So maybe, okay. So I would like you to take write down the equations in a notebook. Now what we are seeing is the intensity of the solar radiation, or what we assume, or what Chapman assumed is, the intensity of radiation will diminish or decrease as it comes down to the lower atmosphere from the infinite or top of the atmosphere, from infinity or top of the atmosphere. So it is losing intensity because there are atmospheric molecules which will absorb the solar radiations, and as a result, the intensity or strength of the solar radiations will continuously reduce. So at a height of the S, the slant height S, the change in intensity with respect to height, di ds is equal to, because this is negative in the means that it is not a negative value, it is decreasing. It is decreasing that I sigma n, where sigma is your absorption coefficient. The absorption coefficient is will vary from species to species. Atomic oxygen will have a separate absorption coefficient from atomic hydrogen, or say from molecular oxygen, etc. So because of its size or each atom or molecule will have a different atmospheric, absorption cross-section. Absorption means how much of radiation it can receive, or how much of this molecule or atom will be seeing the amount of solar radiation which hits that particular atom or molecule. So I sigma n is the total number of atoms or molecules in that particular height. So if the probability of the absorbed radiation will ionize the atom is eta, that means if we consider that ionizing efficiency, that means when the solar radiation hits the atomic species, either atomic or molecular species, it may ionize or it may not ionize. So if the ionizing efficiency is 100%, then all the molecules or atoms hit by the solar radiations will ionize. And efficiency will vary according to the species, as well as according to particularly according to the species. So how many of the atomic oxygen will be converted to oxygen plus and electron minus, that means that will be separated to the oxygen ion and an electron, will depend on the ionizing efficiency. If it is 100%, then all the atomic oxygen in the path of the solar radiation will be ionized. If it is less, then less, okay? So the rate of ionization at height h is therefore Q is equal to eta sigma ni. This is I sigma n, and eta is the ionizing efficiency. So this is the total amount of number of atoms, their absorption coefficient, cross-section, and then this is the intensity of the solar radiation at that particular height. So if the energy absorbed by the unit volume of the gas, sigma ni, this is sigma ni, this is the energy absorbed by unit volume of the gas. Unit volume means, say, 1 centimeter cube. If you talk in terms of meter, then 1 meter cube. So 1 centimeter cube of gas, whatever amount is available in 1 centimeter cube of gas, the energy absorbed by that volume, those atoms, is sigma ni. And therefore, when Q maximizes, dq ds is equal to 0. That means change in the rate of ionization, Q is the rate of ionization. So change in the rate of ionization with respect to height or with respect to distance will be 0. That means there will not be any more ionization. There will not be any more ionization further. Even if you change the height, at exactly at the point of maximum, then you do not get any change in Q. So at the point of maximum, dq ds is equal to 0. So this eta sigma and n is a variable, I is also variable, so we can write it like this: n di ds plus I dn ds. Now, because this eta and sigma, they are not 0, this is 0, left hand term is 0. Eta and sigma are not 0. Therefore, this has to be 0. The term within the parenthesis has to be 0. So we can rearrange it and see that because this is equal to 0, so I can take one term to the right-hand side, make it minus, and then I goes to the denominator of di ds, n goes to the denominator of dn ds, and again rearrange, and you get this equation 4. Okay. Now, m, you have seen a small m here. This m is for the maximum. Maximum means the height at which maximum ionization is taking place. Okay. Now, 1 by n dn ds. 1 by n, I'm taking it from here. The second term in the left-hand side of equation 4, this is 1 by n dn ds. 1 by n ds is equal to dh secant chi. From that figure 1, that chi is there for the zenith angle. So sec chi. So ds is equal to dh secant chi. So cos of chi 1 by n dn dh, or cos of chi divided by h. Now this h, capital H, is a very significant term in atmospheric physics. It is used in low atmosphere also, or wherever gas and molecules or gas dynamics is involved. H is involved. H is also known as the scale height. Scale height, by definition, 1 by n dn dh is equal to h, and this is supposed to be a constant. H is supposed to be a constant, and if you go to the gas laws, this Hargreaves paper, also book, the first few chapters, I think you will find that this H is defined there as equal to kT by mg. You can write K, that Boltzmann's constant, then capital T, m and g. M is the mass, g is acceleration due to gravity, kT by mg. So this appears to be constant, or this is believed to be constant in the atmosphere. Okay, so for a particular temperature, when you are talking about the thermosphere, the atmospheric temperature, we will assume that for a particular height, this atmospheric temperature will remain same. So K is Boltzmann's constant, that is also a constant. Then T, if you keep it fixed, M, mass of the gas, they are available, and Z, acceleration due to gravity. So all this becomes a constant. So that also is given by 1 by n dn dh is also h. Okay, so by definition of h. So from equation 1, if you remember, that is, and now from 1 and 4a, we can write in equation 1, we had this di ds is equal to I sigma nm. 1 by n dn ds is equal to Im cos of chi by hm. Same, 1 by n dn ds, I sigma nm, we are writing this equal to 1 by n dn ds, this one. And you can go back to equation 3 here and equation 1. And by doing that, what you get is di ds. This is m is a subscript only, not a multiple. So di ds m subscript is equal to Im. Im is the intensity of the solar radiation at the height of maximum. Sigma, it doesn't change. Why it doesn't change? Because it is specific to that particular atom or molecule. Absorption coefficient cannot change. So sigma is always constant for that particular species. And Chapman assumed that we have only one species. Maybe that is O. We have only one species. So, and Nm is the number of atoms or molecules at that particular height. that space is at that particular height of maximum. So this is also a constant, Nm, at that particular height. It is a variable that number density of atoms or molecules will vary with height, but at that particular height where you have a maximum, it will definitely be constant. Number of molecules per unit volume will be same. So this is equal to 1 by m d and ds. You can write the equation or you can do it on your own. Then Im cos of chi divided by hm. So what we can write, you can take this hm to here, hm here is equal to, and cos of chi as secant chi, and this is equal to 1. Sigma, this is sigma nm hm secant chi. Im and Im will cancel, Im and Im will cancel. Secant chi is equal to 1. Okay. Now, when the sun is overhead, as we have seen from that figure, when the sun is overhead, chi is equal to 0. Zenith angle is equal to 0. Okay. So sigma, this is equal to 1. So sigma nm hm is equal to 1. Secant chi is equal to 1, for chi is equal to 0. So if h is independent of height, if we assume that m, the mass of the gas is constant throughout this altitude, then h becomes a constant here. Sigma is also a constant. So Nm is proportional to 1 by secant chi, that is cos of chi. Okay. Nm, the number of molecules or atoms at that particular height of maximum ionization, is proportional to the cos of the zenith angle. Okay. So by integrating equation 1, going back to equation 1 again, we can write di by I is equal to integration of from s to infinity, because infinity is the maximum height, s is your height up to which you are measuring. So di by I is equal to minus sigma integration of s to infinity and ds. Okay. So by integrating, we get log of I by I infinity is equal to minus sigma secant chi integration, because this ds is related to dh, we know. So ndh, instead of ds, we are writing in terms of dh, that means the vertical, and that means the change in height with respect to the vertical. And this becomes equal to sigma n goes out, h, if we consider the variation with height to be constant, so it is h secant chi. Okay. So I by I infinity, this is log of I by I infinity is equal to minus sigma and h secant chi. So I by I infinity, or I upon I infinity, becomes equal to exponential minus sigma and h secant chi, exponential minus tau. Okay. So this is another parameter which is very widely used to understand the absorption of radiations in the atmosphere. Okay. Tau is also called the optical depth. Optical depth. This is the depth at which I have written here, if you can see here. Optical depth is a depth from top of the atmosphere to that level where your intensity reduces by 1 by E. 1 by E. 1 by E means this is E 2.78. So 1 by E of its value at the top. That means if I infinity is the value at the top, then I infinity divided by your 2.78, that value of E gives you the optical depth. That means that much depth you can. If I by I infinity is equal to 1 by E, then at tau is equal to 1. If tau is equal to 1, then this, if this is equal to 1, then e to the power minus 1. It becomes e to the power minus 1 or 1 by e. You can see from here, equation 7, I by I infinity is equal to e to the power minus 1 if tau is 1, or 1 by e, 1 by e. So that is the definition. Definition of optical depth is the depth at which the solar radiation reduces by 1 by e times of the radiation at infinite altitude. Okay. Now, coming back to this term, sigma n h secant chi is the optical depth. This is whole term. Sigma n h secant chi is the optical depth and is unity at the level of maximum production. At the level of maximum production, it is unity. Okay. Now, in an exponential atmosphere, what is an exponential atmosphere? We can assume that Chapman has in his assumptions, one of these is the atmosphere is exponentially varying. Exponentially varying means either it increases or decreases. Okay, exponentially it will decrease from a particular maximum. Okay, so if we consider it to be an exponential atmosphere, then the number density of the atoms and molecules is equal to the number density at 0. Number density as 0 means chi is equal to 0, exponential minus h by h, where h is now constant, capital H. Capital H means this, your scale height. Scale height is constant. This small h is the height which is varying. Okay, now you can look at this. N is equal to n naught exponential minus h by h. N naught is a fixed value, maximum. You can consider, say at the height of maximum, n naught is equal to 10 to the power 6. Okay, fix 10 to the power 6. Then from that you can have the amount of electrons, or sorry, amount of those species, either atoms or molecules, at different heights. You can just put this equation and you will find that n is equal to n naught exponential h can give you a shape, parabolic kind of shape. I will show you when I come back to, or when I reach that production term again. That this is an exponentially varying atmosphere. So you consider the atmospheric density or atmospheric concentration to be maximum at a certain height, and from where the atmosphere is exponentially varying. Exponentially varying means which height it will reduce, either to the top or to the bottom. It will reduce. You can have h, minus h, or you can have h below also. Okay. Now, so the maximum rate of production now occurs from equation 5. If you go back to equation 5, sigma n naught exponential minus hm by h secant chi is equal to 1. Equation 5 is this. Sigma nm hm secant chi is equal to 1. So from this equation 5, if I put this n naught instead of n, if I put n naught, then sigma n naught exponential hm by h secant chi. So this is at the height of maximum, where hm is equal to hm is equal to h log of sigma n naught h secant chi is equal to constant plus log of secant chi. You can break these terms within the parenthesis. Sigma is constant, n naught is constant, h is constant. Okay, so all this is constant multiplied by h, again a constant. So this is a constant term, and what you have is only log of secant chi. So this is this. Okay, so hm is equal to constant plus log of secant chi. So from equation 5 and 7, this is 7, I by I infinity exponential minus tau, and 5 is your sigma n h secant chi is equal to 1. So we can get is I by I infinity is equal to exponential minus n by nm. N by nm. Okay? Therefore, Q by Qm, I is related to Q. We have seen I is related to Q. This is production rate. So production rate at any height with respect to the production rate at maximum is equal to eta sigma Ni divided by eta sigma Nm Im. Okay, so break it, N by Nm, I by Im, but I am introducing I infinity again. So I infinity divide and multiply by I infinity. So N by Nm exponential minus N by Nm exponential minus 1. Okay, is it okay? Because Im by I infinity is exponential minus 1. That is the definition of tau. So this is inverse. This is a reverse of this. So it is in the denominator. And I by I infinity is your exponential minus 8. This exponential minus equation 9. So put this in equation 9. Again, n by nm, this is exponential minus h minus hm by h. If you go back and see what is n and what is nm, then the ratio of n by nm becomes equal to exponential minus h hm by h, where hm is the height at the maximum. hm is the height at the maximum, or maximum production, height of maximum production. So h minus hm, therefore q by qm is equal to exponential this term, then exponential e to the power minus h by hm by h, because n by nm, this one, this is here, n by nm, and exponential minus 1. Okay, so this one, from here, and from this, n by nm, you put this exponential minus h minus hm by h here and also here. So you get two exponential terms. Here, within the square bracket, you see exponential minus exponential. Exponential minus h by h, okay? Now, this is, okay. So this is exponential minus h by hm divided by h, exponential minus exponential again, h minus hm by h, and exponential 1, okay? So what is done? This, if I bring it inside exponential, so this is 1, then h minus hm by h, and then again exponential minus h minus hm divided by h. So just rearranging these terms, I get 1 minus this term minus exponential this term, the same term. So this can be written as exponential. If I just want to avoid this writing this whole term again and again, I can do it by putting a kind of another term, say y. So 1 minus 1 y minus exponential minus y. Okay. So what is y? Y is the reduced height. Y is the reduced height. It is a relative height. It is not a constant height. Why it is a relative height? Because it is with reference to a particular height. With reference to a particular height, and reduced height refer to the height of maximum production. HM is the height of maximum production, and your H is the height at which you consider your ionization. It may be above the height of maximum production, it may be below the height of maximum production, and when H is equal to HM, this is equal to 0. So this is also equal to 0, this is also equal to 0, okay? So equation 10 is the Chapman production function. This one, Q by Qm is equal to exponential 1 minus y minus exponential minus y. So this is Chapman's production function, which involves the height of maximum. We are considering with respect to a reference height. The reference height is Hm, and H minus Hm divided by H. This H, as I have said, is the scale height. Is the scale height. We are considering this to be constant within the thermosphere. So this expression 10, you can write it as Q by Qm is equal to exponential 1 minus y minus exponential minus y, or we can do it in a little different way, where we can have, instead of y, we can have a z or z, you can say. This expression can also be derived in terms of the maximum rate of production when the sun is overhead. That means when Qm is equal to Qm naught, you see the difference between these two, or consider the difference between these two. When we were considering equation 10, it is the production, maximum rate of production. We are not saying that it is the solar radiations are vertical. That means suppose let us take the physical condition. Now it is about 11:15 or so. So when your sun is still not overhead, the sun is still not overhead. In the morning at 6 o'clock, it is near the horizon, or 5 o'clock, it is near the horizon. Okay, so it is always a slant angle. The atmosphere, the solar radiations are always at a slant angle with respect to the vertical, or your zenith. Okay, so but even then, at 6 o'clock also you have a maximum production. Maximum means at that particular point of time, you have maximum production. You have production, and which maximizes according to the equations which we have shown. So that Qm can be the maximum production, or Hm can be the maximum production where the solar radiations may not be at the zenith. Okay, so if I consider the sun to be overhead, that means at 12 o'clock, your Qm is equal to Qm naught. That's 0. That 0 means 0 zenith angle. 0 zenith angle. When chi is equal to 0, at a height, Hm is equal to Hm naught. At this point of time, now the height of maximum production is also the height of maximum production when the sun is at the zenith. So again, rearranging the equations, Qm by Qm naught cos of chi, exponential, this is dot, exponential Hm by H, secant chi exponential H naught by H. Okay, so instead of Qm, what we write now, Qz or Qz, you can say. Some people say Z, we say normally Z. So Qz is equal to Qm naught, this one, Qm naught dot secant chi exponential 1 minus H naught by H, secant chi exponential again. You put this from earlier equations, okay? Now here, this is H minus H naught, okay? Earlier it was H minus Hm. For Y it is H minus Hm. We do not know exactly whether this Hm is the height of maximum for when the sun is at the zenith. But now we know that this is the height of maximum when the sun is at the zenith. Okay. So again, going back to earlier equations, 1 minus this minus secant chi exponential again. So QZ by QM naught is equal to exponential 1 minus Z or Z minus exponential minus Z secant chi. Okay. So where you have this Z equal to H minus HM naught divided by H. Okay. If you have been able to write these equations, you will see the difference between this Z and Y. Y, we have taken H minus HM divided by capital H divided by scale height. Here, Z is equal to H minus HM naught divided by H. That means what your consideration is now after equation 10. After equation 10, this is 10 where already we have defined Chapman production function. Okay, equation 10. If you define Chapman production function by this equation, that is also fine. That is also fine, but then you are specifying that your H is or HM is not the zenith height. Height according to the zenith or overhead height. It may be when the sun is at any angle with respect to the zenith. But here we are simplifying this again. We are simplifying this equation, the earlier equations, and trying to see with respect to the height of maximum production when the sun is overhead. Theoretically, it should be. So we'll see from the figure. I will show you a figure. So QZ by QM naught is equal to exponential 1 minus Z minus exponential minus Z secant chi. Okay. So Z is equal to this. So this Chapman production function serves as a basis of reference for ionospheric behavior, and several points about it are worthy of special note. Means, what is this? What is this? QZ by QM naught is exponential 1 minus, same equation. Like QZ by QM naught is equal to exponential 1 minus Y minus exponential minus Y. The same. But here, what we see is HM replaced by HM naught. HM replaced by HM naught. Okay. So Q is equal to, here, this Q is equal to QM naught. This Z actually qualifies the Q, the production rate. Production rate at height Z. QZ is the production rate at height Z. So we may remove that Z from here. So Q is equal to QM naught exponential 1 minus Z minus exponential minus Z secant chi, where Z is the reduced height like before, and chi is the zenith angle of the sun. QM naught is the production rate at the maximum. HM naught is the height at maximum. Height of maximum when the sun is overhead. Height of maximum when the sun is overhead. Okay. So maximum production will be at 6 o'clock also, at 7 o'clock also, at 9 o'clock, 10 o'clock, or maybe in the afternoon also. So always there will be maximum production. But when your sun is overhead, it is supposed to be the maximum of maximum. Okay? Because that chi will not be there. It will not be multiplied by that 1 by cos of chi. So it will maximum production reduced by that value. Okay. So the shape of the curve at great altitudes, Z is large and positive, and Q is equal to Q naught. If Z is very large, this is large, that means if H is very large, then this is a large value, so you will have this equal to Q naught exponential minus Z. This exponential 1, exponential Z, all these terms goes, and this Q becomes nearly equal to or approaches Q naught exponential minus Z if Z is at very high altitude, for flat positive altitude. Similarly, for altitudes below the maximum, so Q is Q exponential then becomes negative below the maximum, so it is less. This is supposed to be okay. This is consider to be 1 kilometer, then 1000 minus 300. So this is the number 700. But if I consider the height below HM, so it will be less than 300. So maybe 250, 200, 100 like that, or even 290 itself is less. So that way your production rate below the maximum, Z is negative because H is less compared to HM naught, and therefore Z becomes negative. Instead of a positive Z, it becomes negative, and you get a rapid cutoff. Okay, so let me go to the figure 2, which I had shown earlier. Okay, from current slide. Okay. So if you see this figure says many things actually. And very common figure. I think it was drawn by Chapman only in their paper, and we are just trying to understand what he used to understand by his production rate mechanism. Okay, so QZ by QM naught. This is the ratio. So this can be 1. This can be 1 at the height of maximum. So sorry. Oh. So is the figure visible? Hello?
Yes, sir, it's visible.
Okay. Then look at the pointer, means cursor here. So because this is a ratio is QZ by QM naught. QM naught is the production at the maximum when the sun is overhead. So it can be 1 and it can be less than 1. Okay, you can see the maximum is 1 and it is reduced 0.5, 0.2, 0.1 and other values, small values. Similarly, your reduced height, that H minus HM naught, this can be also equal to 0. H minus HM naught, if it is suppose if HM naught is 300 kilometer, and if I consider that to be the height of maximum, then that is 0. 300. If H is 300 and HM naught is also 300, then that Z is equal to reduced height, Z is equal to 0. So this is 0. And you should get maximum production there. QZ by QM naught should be equal to 1 at that particular height. You see this curve. Can you see that 0 degree chi? This is chi. This is 0 degree. The lowest curve. If you can see the lowest curve, or if you cannot see, I think you may just have a look at the Hargreaves book or any other book for this figure. You will get it. So this is the curve. I'm going from bottom to top. I'm going from bottom to top. Let us see. This cursor is moving very fast. This is 0. So from here, as we have said, if you increase the height, that means if h increases above hm naught, then also your production rate will decrease. Production rate will decrease. So qz by qm naught will continuously decrease, and it will become small, very small, at a reduced of say 5 or so. That means 5 times of the maximum. If 3 is your 300 is your height of maximum, then maybe around 1500 or so, your production rate becomes equal to 0, kind of, or very small, very small. Now, you can have other values of chi. That means when the sun is not overhead, the shape of the curves remains same. Shape of the curves remains same. Bottom side also. This is 0. Okay, this is 0. So from here, this is the height of production. From top, this is top side, and from here, this is the bottom side. Okay, so at the bottom also, this will reduce with height, but this is negative. So that expression is different. This expression is different. But so here, it reduces very fast. The values reduces very fast compared to what happens at the top. Okay, so bottom side is thicker compared to the top side in Chapman's theory. In Chapman's theory, this is a parabola, but this is not a perfect parabola. You can see from here. This is -2. This is -2, reduced height -2, and this is reduced height 2. So 2 is here, 2 is here, and -2 is here. At a reduced height of 2, you get production or that ratio equal to say 0.4 or something like that. Okay, from here. Okay, 0.4 or 0.3, something like that. But at a reduced height of -2, you get the value of qz by qm naught equal to almost 0. Okay, so as I have said, at the bottom side, because h is negative, it will reduce very fast. The production rate will reduce very fast. So the bottom side of the ionosphere, according to Chapman theory, will be thicker compared to the top side. Top side will have more space or more volume, you can say. More volume, because this is a parabola. So within the parabola, from the height of maximum, you have an area. Below also you have an area. So these two areas, if you compare, this area below is much thicker compared to the area at the top. Okay. So again going back to what we are talking about. So this was figure 2, which we have shown, and as we have seen from the figure, you can draw this figure also. You can explain with this figure, because it is very easy to explain with this figure the Chapman function, that when I is equal to 0, production is always maximum. Qz by qm naught is equal to 1 at the height of maximum, and from where it reduces both on the top side and bottom side according to the equations which you have derived. So if you give another value for chi instead of 0, then also the shape of the curves will remain more or less similar, but it will be always less than q by qm naught. The value will be always less than q by qm naught, because as you have said, Q by QM naught will be multiplied by 1 by secant chi. So that fraction, it will be a fraction of the maximum. That chi will determine how much is reduced, how much of ionization is reduced when you have a slant angle for the solar radiations. So that is why if you look at the curves, if you remember the curves which were shown to you during the seminar and all, and if you also know about this, that the ionization is nearly zero at midnight. Of course, that is there is no sun, but say 6 o'clock in the morning or 5 o'clock in the morning, it is minimum. Then it rises, goes to a maximum around 12 o'clock, and then again comes back to a very low value in the evening. So why it is so? Because of this. At the maximum of ionization, not at maximum of ionization will take place only at the zenith. So that's why during the peak daytime, that means noontime, your ionization should be maximum. Your ionization should be maximum, and when you have chi increasing, the zenith angle increasing in both directions, positive and negative, means towards north or towards south, then also, or east or west, for the sun, east or west, then what will happen? Your value of that Q by QM naught will reduce continuously. And as a result, what you get is a kind of a cosine curve. A cosine curve, because this is cos of chi. So your daily variation should be a kind of a cosine curve, more or less. So if you plot the amount of density according to Chapman, it will be a perfect cosine. Okay, in real life or in reality, in the atmosphere, it is not true. There are other conditions which will come to. Okay. So I leave it here, the Chapman function, loss processes. That is the production. Now we come to loss processes. Okay. Now what is loss? Loss is the amount of ionization. What is amount of ionization plus or minus the amount of recombination, because now ions or electrons have been produced. Okay, it is there. The sun, solar radiations have produced the ions and electrons, but it is also possible because they are chemically active. Because the ions and electrons are chemically active, so chemical reactions can take place between them. An ion, because it is how do they move within the plasma? How will they move? Following your how the ions and electrons will move within the plasma? Do they have any defined path, or will they have any defined path?
Along the field lines.
Oh, no, that will come afterward. Now, say just let us forget about the field lines. Suppose I have a box, and I have atoms and molecules. They are not static, because as long as the temperature is above zero means that zero absolute, they will move. That is what the theory says. So how do they move? These gas molecules or ions and electrons, gas molecules, suppose, how do they move? What is their direction of movement?
It's a random motion.
Random motion. Random motion, there is a particular term for that. Anyone?
Brownian.
Brownian, yes. So they will move randomly, and along the path, there may be some neutrals as well as there may be some ionized species. So if an electron is moving and in its path there is a positive ion, and if both of them collide, that condition is there, if both of them collide, then they will recombine. They will recombine and form an atom, form a neutral atom. So your equation 16, we assume that the electrons recombine directly with positive ions. Assume, they may not, but let us first assume that when an electron hits a positive ion, it immediately becomes a neutral. So the rate of recombination then can be written as L. L is your loss term, Q minus L. Q is production term, L is the loss term. So in your continuity equation, as we have said, or as we now know, the continuity equation normally has both production, loss, and divergence term. Till Chapman, or Chapman's theory, he did not consider the divergence. He did not consider the divergence. So it is only Q minus L. So simple. Simple, maybe because of the time at which or in which this formula was created or reduced, or maybe much knowledge about the movement of the ions and electrons was not available at that particular point of time. So divergence was not included in that in Chapman's theory. You have only Q and L. So it is easier for you. It is easier for you to write Chapman's theory, production and loss. Loss in terms of only recombination plus also two types of recombination. So rate of recombination, this is directly recombined. So rate of recombination is alpha, X plus is that ionized species, and N. N is the total number of atoms or molecules. If it is a molecular species, the molecules. If it is atomic species, atoms. So you can get, this is supposed to be equal. This is supposed to be equal. So alpha N square. This number of ions and number of neutrals are supposed to be equal. So alpha N square. Okay. So L is equal to alpha N square, equation 17, where N is the electron density, and we put X plus is equal to N for bulk charge neutrality. That is what I was talking about earlier also, that the ionosphere is considered to be neutral. So in a large volume, bulk, in a large volume, the amount of ions and amount of neutrals will be equal. Amount of ions or amount of charged particles and amount of neutrals should be equal. Say atomic oxygen. The number of atomic oxygen ionized oxygen species and neutral atomic oxygen species should be equal in number at a particular height. Okay. So considering that neutrality or charge neutrality, alpha is the recombination coefficient. So at equilibrium, del N del T number, rate of change of the number density with respect to time is equal to, this is time, Q minus alpha N square is equal to 0. Production minus loss is equal to 0. Del N del T, this is the equation, continuity equation. So Q minus alpha N square, production minus loss is equal to 0. Therefore, Q is equal to alpha N square, or N is equal to square root of Q by alpha. If Q is given by the Chapman production function, you can put the value of Chapman production function here. N becomes equal to Nm naught exponential square root of 1 minus Z minus this. So from equation 15, you can take Nm is equal to Nm naught cos raised to the power half. That means square root of cos chi. Square root of cos chi. Okay. So such a layer is called alpha Chapman layer. There are two terms. I will come to the second term just now. Alpha Chapman. What is alpha Chapman? Alpha Chapman is the layer, alpha Chapman layer. You note this particular word, alpha Chapman layer. That layer where recombination is dominant. Recombination by direct contact. Recombination by direct contact or direct coming into contact of positive and negative ions. Or you can say positive ions and negative electron. Okay, so this layer is called alpha Chapman because you have an alpha here. You are using this Q minus alpha n square. So this is actually the production number density at any given time for the alpha Chapman layer, where Q is equal to alpha n square. Alpha is your recombination coefficient. Recombination. Okay, so where you consider the loss to be only due to recombination, the Chapman layer is alpha Chapman. So you can write it here that when we consider the loss to be only due to recombination, that is the term where alpha is the recombination coefficient, the layer is called, or that stretch of ionosphere will be called alpha Chapman recombination. Okay, so another assumption you can have is the ion or electron, they may not hit, means recombine directly, but what may happen, your alternative assumption, electrons are removed by attachment to the neutrals as like this. So this electron, any electron, moving Brownian motion, moving at random and hitting a neutral atom. So what will happen if it hits and combine with the neutral atom, ionize that atom, negatively ionize. So this E, this M becomes M plus, okay? So the rate of attachment is now attachment. They the electron is attached to the neutral. So in this case, we call that coefficient as beta. L is equal to beta n directly. So the above equation, also known as recombination, Breast recombination law. So what happens? Beta is a function of altitude as the number of neutrals exponentially decreases with altitude. So beta becomes a function of altitude. Beta, because it is related to not ionic species, but it is related to molecular species or neutrals. So neutrals, as we know, will continue to decrease with altitude. Okay, so beta becomes a function of altitude, and therefore this Q is equal to beta n. Q minus beta n, actually, del n del T is equal to Q minus beta n. Q minus alpha n square for alpha Chapman, and Q is equal to beta n or Q minus beta n for beta Chapman. So again, the same Nm is equal to exponential this, and also the same function, but in this case, your layer is called beta Chapman layer. Beta Chapman. So equation 20, that is alpha Chapman, and equation 25 here provide experimental test about whether a given ionospheric layer is alpha or beta Chapman type. Okay, whether you have a direct recombination or you have a two-way recombination process in which the ionic species hits a neutral, ionizes the neutral, and then it recombines. So that way, loss process is different. Loss process is different in this case. In case of beta, the loss process is different in case of alpha. In case of alpha, direct recombination. In case of beta, not between alpha and beta, not between a charged particle, two charged particles, but between a charged particle and a neutral, So one charged particle making another charged particle. So beta layer will be defined from the alpha layer, where recombination takes place, and when recombination takes place, you get neutrals. But here, neutrals are converted. So this beta layer will have, in terms of ionization, will be different compared to the alpha layer. Okay, so so you can have another equation. Say we have X plus, then you have a molecular species A2, then that molecular species dissociate to two atoms A and A, but that A recombines with that X plus. So recombination of ion and electron, AX plus E becomes A and X. So this way also you can have recombination. Okay, instead of one species, if you have a molecule, instead of one atom, if you have a molecule dissociated into two, then you can have one recombining with an ion and the other remaining neutral, then ion again recombining with an electron, becoming A and A. So 2A, this A2 remains as A and this X plus in the process becomes X. Okay, so ionization is lost. This ion is lost through this process. If you look at this, X plus plus A2, A converted to A and A, dissociated by energetic radiations. They can dissociate atoms, molecules into atoms. So A and A can form, and one A can combine with because they will be in a excited state, so they can combine with an ion, so become this, and this in the process can again recombine with an electron to become A and X. So that molecule will remain same, two atoms, but you have neutralized the other molecule, other atom in that process. During that process, you have neutralized this. So that is loss. So here, A2 is a common molecular species such as O2 or N2. Here, it can be O2 or N2. And in the first step, the positive charge is exchanged. What I have told you. So this is this. So you can write these equations. Now, what happens here? So here, this equation I, 26I, okay? Or I or 1, say. 26, 1, you can say X plus A2 is equal to AX plus A. So this is beta X plus. Beta X plus, loss, and 2 is alpha AX plus N. Okay? So at low latitudes, beta is large, low altitude, sorry. Beta is large and X is rapidly converted to AX plus. This point beta is large at low altitudes. That means recombination by combining with a neutral. That means the first dissociation of one neutral molecule to two neutral atoms, and then getting the charged particles to combine, and then getting again to neutral, going to neutral. That process, beta beta process is large at low altitudes. Low altitudes means, say, 100 kilometer, 200 kilometer or so. At the bottom side, beta is large. Whereas, because this x rapidly converted to ax plus, this one. The overall rate is then controlled by 2, and one expects to find an alpha type process because this for charge neutrality. So first your reaction beta type takes place, and then you get alpha type reaction. Similarly, at high altitudes, beta is small, beta is not large, beta is small. So one is relatively slow, very slow, and the controls the overall rate. Now x plus is equal to n, and we have a beta type process. The behavior therefore changes from alpha type to beta type as the height increases. So look at this. Look at these few lines. When you have two different loss processes, one is beta type, the other is alpha type. Alpha Chapman, beta Chapman. Now from here, have you imagined where will be the beta layer and where will be the alpha layer? Alpha is bottom, or alpha is at top, or beta is at bottom, or beta is at top?
Beta is at bottom.
Huh?
Beta is at bottom.
Beta is not at bottom. Beta will be at top. Because what is happening, as I have said, at low altitudes, beta is large, very quick. And x rapidly converts into ax. This first line. At low altitudes, beta is large, and x means the neutral atom. X is neutral atom, is rapidly converted into ax plus. Okay? So the overall rate is then controlled by the equation 2. Equation 2. And one expects to find an alpha type process because ax plus is equal to n for charge neutrality. For charge neutrality, you will have ax plus is equal to n, which we have shown earlier. For alpha type process, ax plus is equal to n. Okay? So that means this 2, this is neutral. This becomes equal to number of neutral atoms. This also becomes ax plus. X plus is the ion, so neutral combines and equal to n. So at high, so this is for low altitudes. Low altitudes, beta is large, the reaction proceeds quickly, and then alpha takes over. But at high altitudes, beta is very slow. Beta is very slow because you do not have many neutrals. The neutrals are less at high altitudes, so beta is a slow process. And therefore, the behavior then changes from alpha type to beta type as the height increases. Relatively slow and controls the overall rate. Alpha cannot overcome the beta at high altitudes because the rate is slow. Beta is slow. At high altitudes, beta is small. So equation 1 is relatively slow and controls the overall rate. Let us see what is equation 1. This one. This one. X plus A2, ax plus A. Why it is slow? Because A2, number of neutral molecules are less at higher altitudes. So the reaction itself will take more time. That means for that this ion to reach one molecule will take time, and therefore the process will be slow. And this recombination ax plus E, then equation 2 does not take place there. So x plus is equal to n, and we have a beta type process. There, x plus is equal to n. At lower heights, ax plus is equal to n. At lower heights, ax plus is equal to n, whereas at higher heights or higher altitudes, x plus is equal to n. Number of ions is equal to number of neutrons. That is when what we considered when we talked about alpha Chapman. But here, in this case, at lower altitudes, this is higher altitude. At lower altitudes, it is ax plus is equal to n. That means the atomic species attached to the ion is equal to n. One atomic species attached to one ion, say one O attached to one O plus. Okay, so that becomes equal to the number of atoms, neutral atoms. So at just for our understanding sake, or sake of understanding, what we will consider or what we will keep in mind is that beta type of reaction is dominant at higher altitudes, whereas alpha type of reactions or recombination will be at lower altitudes. You can put for this A and other things, you can put O and n by 2 or O2, and you can see how these equations can vary. Okay. So when it is in equilibrium, 1 by Q becomes equal to 1 by beta n, this H is height, plus 1 by alpha n square. This is Q is production, this is loss, and this is also loss. Okay, so transition from alpha to beta behavior occurs at transition height ht, where this one is equal to this alpha n. N and n will cancel, so beta ht is equal to alpha n. 1n will cancel, so here 1n will remain. So beta becomes equal to alpha n at the transition height. Okay. Now below ht, only second term in below ht means transition height. This term is important. Above ht, the other term is important. So that is how you see alpha Chapman and beta Chapman. Okay. Once you consider the equilibrium case, this is the equilibrium where both are equal. Say this term, this production is equal to loss, and this loss term is also equal to this loss term. Then transition between these two, that means exactly where alpha changes to beta or beta changes to alpha, is where the height is equal to ht, transition height. Okay, and at that height, this becomes equal to this and this. So n and 1n cancels. So beta becomes equal to alpha n, not alpha. Beta becomes equal to alpha n, and below ht, you can see below ht, this is the dominant term. Second term is dominant, and q is equal to alpha n square, because this process is very fast. So this is in the denominator. So you get a very small value for this, and you get a large value for alpha n square equal to q. So q becomes alpha n square. Similarly, for lower, higher heights, q is equal to beta h. So equation 29 are applicable at all heights of the electron distribution. Will be figure 6b. I have not considered those figures. I do not have those figures, but this is what you can see from here. If I consider the molecular species N2 and atomic species O, then the transition height between O and N2 is equal to 1.75. The ratio of HO divided by HN2 is equal to 1.75. So N is equal to exponential 0.75 HO. If you consider these two spaces, if you consider other spaces, it will be different. Okay, I think we can discuss a little more about this formation of alpha and beta layers. Equations we have done. I would like to stop here for today. Equations we have done. The physics again or the process again. We'll try to understand a little in our next class, and then we go to what I have put here as ionospheric layers. Ionospheric layers as they exist, not this alpha Chapman or beta Chapman. Okay, alpha Chapman and beta Chapman are okay. This is according to Chapman's theory, and Chapman has deduced that the recombination or the loss process is different at different heights. Means it is a direct recombination process at lower heights, and at upper heights the recombination is low. So this is true. This is still true. If your ionosphere goes up, say production is maximum at 300 kilometer, maximum production has occurred, and somehow because of some process it has gone up to 400 kilometer. Then that whole amount of ionization will be reduced slowly. Okay, as it goes up, that is beta Chapman. As it goes up, the process itself, the recombination process itself will be slower. But if it comes down, say if from 300 kilometer it comes down to 200 kilometer, as we have seen now or considered, it will be an alpha Chapman kind of thing. The recombination will be very fast, and your amount of ionization will also reduce that fast or quickly. Okay, so movement of ionization up and down vertically changes the nature of the amount of ionization. If it goes up, this is a physical process. It has a very important physical meaning, that if it goes up, the ionization will remain as in the ionized state for a longer period of time. If it comes down from the maximum, it will reduce fast. That means the amount of ions or electrons will be coming or becoming less and less very quickly. Say quickly is a relative term, slowly is also a relative term, but if somehow by some process, suppose some process passes the ionosphere to lower heights, then it will recombine fast. The ionization will disappear fast. But if it goes up, the ionization will not disappear fast. It will be there for some more time, compared to what it was at the height of maximum. At the height of maximum, say 300 kilometer, the ions and electrons, they are recombining at a rate of 0.5. 0.5, it is not 1, say, suppose, QM not. So if it goes up, the 0.5, maybe 0.4 or 0.3, but if it comes less, if it comes to lower heights, it may be 0.6 or 0.7 or maybe more. So very fast. Recombination, I am talking about that recombination. So these physical processes take place, and Chapman could see or visualize that these processes will be different. The processes will be different in the ionosphere, and recombination will be less at lower heights. The loss will be less at lower heights. The loss will be more at upper heights, and loss will be more at lower heights. That is why from those graphs also, the figure 2, if you remember, that the same equations we are using. So the production rate, the ratio of the production rates becomes very, very low or very small quickly compared to what it is above. Okay. So I think we can conclude here for today. Questions, you can put it in the chat box also if you or if you have any. You can talk also. Let us see if you have any questions. I have been a little fast, but because these are equations, I think all of you will be very quickly going through it. It won't take much time for you to understand the flow of these equations or Chapman function. 1935 he deduced these equations. So now we are in 2022. We should be faster. Am I right? Any questions, or if alpha Chapman, beta Chapman, without taking into consideration the divergence or the transport processes. Keep that in mind. So, no questions?
About questions.
Hello, sir.
Yes.
Hello.
Yes, yes.
Hello, sir.
Yes.
আজি question hello এটা নাই মাজতে সুধিলে
Acha. Okay. So this is a kind of a two-way process. Either everything is understood or nothing is understood.
nothing